Okay, I'm going to be working on the chain rule here, 11.4, and starting out with number 9. So here it says, replace the question mark with an expression that will make the indicated equation valid. So it says here, we want to take the derivative with respect to x of 3x plus 4, and then that quantity is going to be raised to the 4th power. Then they say that that's equal to 4 and then 3x plus 4 cubed, and then they want us to fill this in right here. So we want to make sure we understand that the chain rule is telling us that we can treat this almost like a power rule. We have something here that's being raised to the 4th power. So the 4 is going to come out in front. Then we're going to rewrite whatever was here. We're going to reduce the power by 1, which becomes 3. And then the very important part of the chain rule is that now you have to tack on multiplication, and now you take the derivative of what's inside. So the derivative of 3x is 3, and then I would have plus, and then the derivative of 4, which is 0, so I don't need to write anything else. So that's it, 3. Now you could clean this up if you wanted to. You could take that 3 and put it out here with that 4, make that a 12, then 3x plus 4 cubed. That would be a more appropriate answer. All right, now number 11, similar setup. Want the derivative with respect to x of 4 minus 2x squared cubed. 4 minus 2x squared cubed, and that's equal to 3, and 4 minus 2x squared, and then cubed, squared. And then times, now they want us to fill this in. So same thing, we have like a power rule here. We have something to the 3rd power, the 3 comes out front. We rewrite this base right here. We reduce the power from 3 to 2, so we subtracted 1. And then the very important step, we need to multiply that times the derivative of what's in here. The derivative of 4 is 0, so there's nothing for that. And then derivative of negative 2x squared is the good old power rule. We just drop the 2 out front. It becomes negative 4 because negative 2 times that 2 is negative 4. We reduce the power by 1, that's x to the 1st power, so I can just do like that. Now this is being multiplied, okay? So what I'm going to do is I'm just going to pull this and drop it out front. That 3 and the negative 4 become a negative 12. The x that's here is going to just sit there in front. Then I have 4 minus 2x squared squared. So that would be our result. All right, let's move on. Number 17. So for 17, we have a function f of x is equal to 5 minus 2x raised to the 4th power. And we want to take the derivative using the chain rule and simplify. So with our derivative, give me just a second here to answer this. Okay, so we notice that we have this expression raised to the 4th power. So I'm going to use like that generalized power rule. I'm going to bring the 4 out. I'm going to rewrite 5 minus 2x without touching it, and then reduce the power by 1. Then multiply that times this derivative. Derivative of 5 is 0, and the derivative of negative 2x is just negative 2. So I'll put negative 2 there. It's being multiplied, not subtracted, so that multiplication can come out. Multiply that 4, comes negative 8, 5 minus 2x to the 3rd. That's it. Number 19, f of x equals 4 plus 0.2x to the 5th. All right, so same thing. Derivative of this is equal to, well, we have something here raised to a power. So we're going to pull that power out front, 5. We're going to rewrite what we have. We're not going to touch it. Reduce the power by 1. And then multiply times the derivative of what was in here. So derivative of 4 is 0. Derivative of 0.2x. Remember, the derivative of x is 1, and the constant just comes for the rise. So this is just going to be 0.2. And that gives us, we have to multiply the 0.2 times the 5, and when you do 0.2 times 5, you get 1. So you don't need to write that 1 out there. You can just write whatever was left, which is this. Okay. Number 21, 3x squared plus 5. 3x squared plus 5 to the 5th power. And this is number 21. So we want to do f prime of x here. Same situation. F prime of x is the 5 comes out. So this raised to the 5th, 5 comes out. We rewrite this, don't touch it. And then reduce the power by 1. Now multiply times the derivative of what's in here. Derivative of 3x squared, the 2 comes out, hits the 3, becomes a 6. Power on the x comes down by 1, so it just becomes x to the 1st power. Then plus the derivative of 5, which is 0, so there's nothing else to put out there. And then I can multiply these together. 6 times 5 is 30. The x is just going to sit there in front, and then I have 3x squared plus 5 to the 4th. All right, number 29. 2x minus 5 to the 1/2. 2x minus 5 to the 1/2. And this is number 29. We're kind of got a, I want to say a scratch record we're skipping, but who listens to records? Okay, we have something here raised to the 1/2. So the only difference in this one is that we got a fraction up here, but we follow the same format. The 1/2 comes out. We have 2x minus 5. We reduce the power by 1, so we subtract 1 from that, we get negative 1/2. And then we multiply times the derivative of what's in here. Derivative of 2x is 2, derivative of 5 is 0. So I'm just going to throw a 2 here. I'm going to bring that 2 out into the front there. 1/2 of 2 is 1, so they basically just cancel each other out. And then you have 2x minus 5 to the negative 1/2. That's perfectly acceptable. You could, if you wanted to, rewrite that as 1 over 2x minus 5 to the positive 1/2. If you didn't want the negative exponent, you could drop this down as a positive. Okay. Number 31, x to the 4th plus 1. X to the 4th plus 1 to the negative 2. It's number 31. All right, so we have same thing. We're just going to come in here, take this, we're going to drop the power out front, negative 2, x to the 4th plus 1. We subtract 1 from this, so negative 2, take away 1, that's negative 3. So be careful there. This is negative 3 times the derivative of what's in here. Derivative of x to the 4th is 4x cubed, and then plus 0 because the derivative of 1 is 0. So this is sitting out here. I'm again going to move it out here. I've got negative 2 times 4, which can give me negative 8. The x cubed is going to sit out front. And I have x to the 4th plus 1, all of that raised to the negative 3. All right, let's look at number 45. Number 45, you've got y equals 3, then parentheses, x squared minus 2 to the 4th. Wait, x squared minus 2 to the 4th. All right, so we have a slight little change here. We're trying to find y prime. The difference is that we've got this 3 here. A lot of the problems we've been doing have been pretty much like this. The 3 is going to have very little impact. Because it's a constant attached to a function, all that happens to that when we take the derivative is that it just comes for the ride. So we're going to go 3 times, and now let me take the derivative of this. So I use my chain rule again. The 4 is going to pop down. Then I have my x squared minus 2. I'm going to reduce the power by 1. And then chain rule says multiply times the derivative of what's in here. Derivative of what's in there is just 2x. And now I can bring this 2x out to the front. I already had a 3 times 4, which was 12, but then I have to hit that with a 2 and an x. So that should become 24x. Then I still have x squared minus 2 to the 3rd power. So all that happened is that 3 just kind of hung out in the front and multiplied everything at the end. All right, number 47. They want the derivative of, so that just means we want the derivative treating x, oh, it's t. They want the derivative of this treating t like the variable, and they have 2, and then t squared plus 3t, all raised to the negative 3. All right, this one's interesting. All right, so the derivative of this is, well, this 2 again is multiplied times all of this, so the 2 is going to come for the ride. And now I'm going to take derivative of this, and it's to the negative 3. So the negative 3 pops out front, negative 3. I rewrite t squared plus 3t. I don't touch it. I subtract 1 from that, I get negative 4. And then I multiply times the derivative of what's in here. This is going to be a little different. Derivative of this is going to be 2t, but then I have plus the derivative of this, which is just 3. And I have 2 terms here, so I must put these in parentheses in order for this to be correct. And then I will put 2 times negative 3 together and get negative 6. And then I'll have t squared plus 3t, all raised to the negative 4. And then I still have that 2t plus 3 sitting off the end there. All right, number 49. dH they want us to find dH dW, and they give us that h of w equals square root of w squared plus 8. All right, now this may look weird because they're using this, these different letters, but this may as well be like f of x equals square root of x squared plus 8. So just replace all your w's with x's, replace h with f, and this is what we would have. And then over here, if we replace h with f and w with x, this is really asking us for derivative of f with respect to x, which is our standard derivative. Okay, so they want us to basically take derivative of this. Just notice that we have w instead of x. So dH dW should be equal to, also let me do something here. I need to rewrite this. This original function should be rewritten as w squared plus 8, that entire quantity to the half. So I'm just rewriting what the root means. It's the half power. And then I can do that same thing. I've got something to a power, power comes out. So here it comes. 1/2 drops out. I've got w squared plus 8. I subtract 1 from this, I get negative 1/2. And then times the derivative of what's in here. Derivative of that is just 2w, right? Because the derivative of 8 is 0. So I've got that sitting here. That's a negative 1/2 right there. And I can just kind of slap this out to the front. Half of 2 is 1, but I still have a w. So how about w, and then w squared plus 8 to the negative 1/2. Now I've noticed in the answers in the book, anytime they've had a negative exponent, they've dropped it down. So like the book is going to do this over w squared plus 8 to the positive 1/2. And they could even go a little further and just rewrite, kind of like using the fact that the 1/2 means square root. You could rewrite that as square root of w squared plus 8. So that might be how the book has it in the back. All right, now 59. We have dw, so I want to take the derivative. We're treating w as our variable, and we're trying to take ddw of 1 over w cubed plus 4 to the 5th. Make sure I got that right. Yes. All right, now before I can do anything, I need to first try and rewrite this. So I want this derivative dw, I want to rewrite this as w cubed plus 4 to the negative 5. So what I'm doing is I'm bringing this up as a negative power. Then I can use my generalized power rule, which is allowing me to take this, then drop my power out. So here we go, derivative time. Negative 5 is going to pop out. We're going to have w cubed plus 4, not touching that. Subtracting 1 from negative 5 is negative 6. Be careful there. And then the all-important multiplication of the derivative of what's in here. So derivative of w cubed is 3w squared, and derivative of 4 is 0. So I can just leave that like that. And then slide that out front. That's going to be negative 15w squared, then w cubed plus 4 to the negative 6. I'm sure that the book will drop that down. That negative 6 power, they'll drop that whole piece down here and leave these pieces up top. $79. All right, we want ddx, so we want the derivative of this. X is our variable. And we have the expression 3x, and then x squared plus 1 cubed. All right, this one's a little tricky. All right, because we've got this 3x in front, that's not just a constant. It's actually a constant times a function, and then times more function. So we can't just bring the 3 for the ride. Well, we're not going to bring the 3 for the ride. We're going to notice that we have multiplication right there. And then that means that this piece is like our f, and this piece is like our g, and we have the product rule here. So the derivative of f times g is f prime times g plus g prime times f. So basically, I'm going to just use that formula, and I'm just going to rewrite everything here. So we need to know what the derivative of f times g is. So it's going to be the derivative of f, which is derivative of just 3x, which is 3, times g with no derivative. Here's g. So we have x squared plus 1 cubed, plus, now here's the hard part, the derivative of g. Now this is g right here, the whole thing. So if I were to have just started the problem out and gave you this problem, forget everything else, and I ask you for the derivative of this, you're going to do what we've been doing. You're going to say, okay, well, the 3 drops out front, x squared plus 1, you're going to reduce the power, then times the derivative of what's inside, which would be 2x. And then you bring that out front, and you get 6x, x squared plus 1 squared. So the derivative of this is this. And that is what g is. So in the formula right here, g prime, we actually just want to slap this in there. So 6x, and then x squared plus 1 squared. And then we have to finish off the formula, times f. And that's f, it's 3x, so times 3x. And now we just clean this up a little bit. We have 3x squared plus 1 cubed. And notice here we could bring this 3x up to the front. That would become plus 3 times 6 is 18. And then we have x and x, so that's going to become x squared. And then we already had x squared plus 1 squared. And that's good enough. They might go a little further, but I think that's good enough for what we're doing. All right, now the last problem is a word problem. The last one is number 91. It says that the drug concentrate, oh, wrong one, sorry. The total cost in hundreds of dollars of producing X cell phones per day is given by the following function. C of X equals 10 plus square root of 2x plus 16, and X is between 0 and 50. So X is the number of cell phones per day. Number of cell phones that were, so number of cell phones produced per day. And then, of course, C of X is the cost in hundreds of dollars. So C of X, the value of this function is the cost in hundreds of dollars of producing exactly X cell phones per day. So this company has certain cost to produce cell phones. If we produce 10, wait, was this supposed to be 50? It's supposed to be 50, sorry. So if we produce 10 cell phones per day, we plug 10 in here to give us the cost. And that cost would be in hundreds of dollars. So what do they want us to do here? They want us, part A, to find C prime of X. So C prime of X, what we're going to do is we're going to look at this here. We have this plus this. So we have two terms. We take derivative of each one separately. Now, I think before I do the derivative, let me go back up here and rewrite this. Just remember that this is really the same as this. So I'm converting the radical over to the fractional exponent there. So now when I take the derivative of 10 is 0. I'm going to write it even though we don't need to. Plus, now, derivative of this, we have this to a power. We bring the 1/2 out. We've done this a lot now. Subtract 1 from up there. Times the derivative of what's in here, which is just 2. And this half and this 2 cancel. And the 0 again out front doesn't matter. So all we have is 2x plus 6 to the negative 1/2. I'm going to go ahead and drop that down as 2x plus 6 to the positive 1/2. And I'm going to rewrite that as square root of 2x plus 6. So this is our derivative. This is the derivative of the cost function. And now it wants us to find f prime of 24 and f prime of 42. I said f prime, I meant c prime, sorry. So for part B, we want c prime of 24, which means all we're going to do is replace this x with 24 into our derivative. So we go 1 over square root. 2 times 24 is 48 plus 6, which is 1 over square root of, unfortunately, 54. And I'm going to need to do that on my calculator. So 1 divided by the square root of 54 which is approximately 0.136. All right, now let's do C prime of 42. C prime of 42, which is going to be 1 over square root of, now I'm plugging 2 times 42 is 84 plus 6, which is 90. So I get 1 over the square root of 90, which is approximately 0.105. So let's interpret these results. What do they mean? Well, C prime of 24 means that if, or at a production level, I need to erase this, at a production level of 24 phones a day, our cost is increasing by 0.136 $100 a day. Okay, so what does this mean? 0.136 $100. Remember, everything was measured in $100. So I try and make this a little bit easier. What if this number was 2, right? Then that would be the cost is increasing by $200 per day. If we say 0.2, right? And, well, let me do it with 1. Okay, it might be easier. If I said 1, that would mean that our cost is increasing by $100 per day. If I say 0.1, instead of $0.100, I could look at that as a tenth of $100. So this is really like the fraction 1/10 of $100, which would only mean $10. Okay, so this means $10. So this right here, what's basically happening is we're moving our decimal point, that's all. So this means that we're actually increasing at a production level of 24 phones a day. Our cost is increasing, so our cost is going up by not $0.100, but we could just convert this over to $13.60 a day. But our cost is increasing, okay? Our cost is going up because it's a positive number. At 42 phones, all right, we get this answer. So the only difference is that at a production level of 42, the cost is still increasing because it's a positive number, but instead of $13.60 a day, it's going up by $10.50 a day. So you can see by producing more phones, the rate at which our cost is going up is actually lower here. So we would probably want to be producing more phones. Even though our cost is going to go up, the rate at which it's going up is smaller. So we're not spending as much money to produce more phones. Or the rate at which we're spending money is not as fast. Okay, that covers this section, 11.4.